Let us solve the equation x² + y into x+y² equal to x minus y whole thing cube. So we want to solve this equation in integers x and y. Let's write the equation once again. x² + y into x+y² equal to x minus y whole thing cube. Let's write this one as equation 1. So we want to solve this equation in integer. You see that we have got two variables x and y and just one equation. So we might expect to get infinitely many solutions, but the restriction that x and y are integers reduces the number of solutions drastically. Let's see how. We apply distributive law. x² into x is x cube, x² into y² as it is. Sorry, x² into y². Y into x, that is same as x into y. Then y into y² is y cube. What about right hand side? That's a simple expression, x minus y whole thing cube. That's equal to x cube minus y cube minus 3x² into y plus 3x into y². Let's write everything to the left hand side. Oh, we can see that x cube can be cancelled. So we cancel x cube out. Then y cube plus y cube. So we can write it as 2y cube plus x² y² plus xy. Let's take everything to the left hand side. Y cube we already took it. Minus 3x² into y. That gives us plus 3x²y minus 3xy² equal to 0. Okay. So you can see that you can take y common. Let's take y common. When we take y common, we are left out with 2y² and then x² into y. This one just x. This one again, not again, 3x². And then if I take y common, I am left out with 3xy equal to 0. Now if product of two numbers equal to 0, then one of them has to be equal to 0. Maybe both of them are 0. So it must happen that either y equal to 0 or this whole expression equal to 0. Maybe both are 0. Let's look at the easier case. If y equal to 0. Okay, we write y equal to 0 in equation 1. So x² plus 0 into x plus 0 equal to x minus 0 whole thing cube. Is that true? Yeah, which is true. Which is true. Well, x² into x is x cube and x cube is equal to x cube. That is true for any real number or even for complex number. But we were looking for only integer x. We are looking for only integers x comma y. So what do we say that which is true for every integer x? Okay, therefore x comma y equal to x comma 0 is a solution for every integer x. So what we have achieved so far is a trivial solution, x comma 0. It is a solution of equation 1. What about other solution? Let's look at the other case. If y were not equal to 0, this quantity must be 0. So if 2y² plus x² into y, let's write minus 3xy, just shift this position, and then plus x plus 3x² equal to 0. Now we can see that we can write something like a coefficient of y², a coefficient of y, then a term that do not involve y. That reminds us about quadratic equation. Once again, a coefficient of y² and then x² minus 3x times y, a coefficient of y, and then x plus 3x square, a quantity that do not involve y. Now we can regard this as a quadratic equation, and as we have said earlier, we want integer solution x and y. Now a quadratic equation will quadratic equation will give you integer solution only if let's write it in standard form, ay square plus by plus c equal to 0. Only b square minus 4ac is a perfect square. So quadratic equation with let's say integer coefficient will give us a integer solution if and only b square minus, not if and only, if b square minus 4ac is a perfect square. So it must happen that this quantity b square minus 4ac is a perfect square. Therefore x square minus 3x whole thing square minus 4 into 2 into x plus 3x square minus 4ac must be a perfect square. Must. So we expect that x square minus 3x whole thing square minus 8 into x plus 3x square is a perfect square. But let's try to manipulate this expression. So again we have a minus b whole thing square. So that's equal to a square. X square whole thing square is x to the power 4 plus b square. So 9x square minus 2 into x square into 3x minus 8x minus 8 into 3 is 24x square. Okay, so that's equal to x to the power 4 minus 6x cube and then minus 15x square minus 8x. Well, you can see that we can take x common. Let's take x common. So this is equal to x into x cube minus 6x square minus 15x minus 8. Okay, can we factorize this expression? If I can factorize, maybe simple factor, if simple factor exists, like x equal to 1 or x minus 1 or x minus 2 or x plus 1 or x plus 2, then it must be some integer must satisfy this equation. Definitely x equal to 1 will not satisfy this equation. What about x equal to minus 1? Minus 1 cube is minus 1. Minus 1 square is 1. So minus 6 minus 15 minus 8. Oh sorry, if I write x equal to minus 1, this is plus 15. 6 plus 8 is 14. 14 plus 1 is 15. 15 minus 15 is 0. Okay. You see that x equal to 1 is a solution of this expression. So we observe that if we write x equal to minus 1, then this quantity vanishes. So it must happen that x plus 1 is a factor. So let's try to factorize it. I want x plus 1 to be a factor. So x cube plus x square. Definitely I can take x plus 1 factor here. But I have to maintain the equality. Coefficient of x square is minus 6, but I am writing plus 1. So better write minus 7x square. Minus 7 plus 1 is minus 6. So we are maintaining the coefficient of x square as well as coefficient of x cube. What about coefficient of x? Again, I want x plus 1 as factor. I know that x plus 1 is a factor. So I have to write minus 7x. Definitely I can take x plus 1 as a factor here. But when I write minus 7x, but coefficient of x is minus 15, so to adjust it, I have to write minus 8x. Minus 7 and minus 8 will give you minus 15. Fine, minus 8 we write it as it is. Now you can see that I can take x plus 1 common. Okay, upon taking x plus 1 common, we get x into x plus 1 we take common. X square minus 7x minus 8. Oh, this is a quadratic expression and we can definitely factorize it. So this is equal to x into x plus 1 into our expression. Now we know that we can factorize it by splitting the middle term. So x square minus 7 can be written as minus 8 plus 1. So minus 8x plus 1x. We are breaking minus 7 is minus 8 plus 1. And minus 8 into 1 is minus 8. So we are in the track. X into x plus 1. We take x minus 8 common and we are left out with x plus 1. Well done. Oh, we want this expression to be a perfect square. Remember that? Yeah, we want this expression to be a perfect square. X into x plus 1 into x minus 8 into x plus 1. But we have x plus 1 whole thing square here. X into x minus 8 into x plus 1 whole thing square. That's already a perfect square, but not this x into x minus 8. Therefore, we must have that. Therefore, it follows that x into x minus 8 is a perfect square. So let x into x minus 8 equal to z square. It is a perfect square, so it must be equal to z square for some integer z. Can we solve for z? Maybe. Let's try. This implies x square minus 8x equal to z square. Now x square minus 8x, I can render it to be a perfect square simply by adding 4 square. But that will not maintain the equality, so I have to add 4 square to the right hand side. So that's correct now. So we can write this as x minus 4 whole thing square. A minus b whole thing square is a square minus 2 into a into b. 2 into x into minus 4, that is minus 8x plus b square. Fine. Equal to z square minus, plus 16. Let's take z square to the left hand side. So variables, we write it to the left hand side. Not only that, left hand side is a difference of square. So we know the formula that a square minus b square, a square minus b square equal to a minus b into a plus b. So this implies x minus 4 minus z a minus b into a plus b. X minus 4 plus z equal to 16. Now x minus 4 plus z, that's an integer, correct? That's an integer. What about x minus 4 plus z? That's an integer. X minus 4 minus z, it is also an integer. Yes, x and z are integer. Both are integer. So you see that integer into integer equal to 16. So, but 16 has got limited number of factors. What are those? Let's write those one by one. So far we observe that x minus 4 minus z is a factor of 16, but the only possible factors of 16 are plus minus 1. We are talking of integer factors, so plus 1 as well as minus 1, then plus minus 2, then plus minus 4 and plus minus 16. But if x minus 4 minus z is plus 1, then x minus 4 plus z must be 16. So x minus 4 plus z equal to, when it is plus 1, this has to be plus 16. When it is minus 1, this has to be minus 16. So plus minus 16. Depending on that, if this is positive, this also has to be positive. If this is negative, this one also has to be negative. 2 plus minus, oh, I forgot plus minus 8 here. 1, 2, 4, 8, 16. 2 plus minus 8. 4 plus minus 4, 8 plus minus 2, 16 plus minus 1. Okay, so far so good. Let us add this to equation. X and x will get 2x, minus 4 and minus 4 minus 8 equal, z and minus z will get cancelled. If we add 1 with 16, you will get 17, minus 1 and minus 16 minus 17, 2 plus 8, 10 and minus 10, 4 plus 4, 8 and minus 8, 8 plus 2 is 10, minus 10, 16 plus 1 is 17, minus 16 and minus 1 is minus 17. Now you see that now left hand side is positive, so 17 is not possible. So these are not possible. So it follows that if I take 2 common and divide by 2, x minus 4 equal to 5 minus 5, 4 minus 4. Why should I write again 5 minus 5? So these are the only possibility. That imply x equal to, we just add 4 to both sides. 5 plus 4 is 9, minus 5 plus 4 is minus 1, 4 plus 4 is 8, minus 4 plus 4 is 0. Oh, let's look at the easier case, x equal to 0. Case 1, x equal to 0. Let us write this equation as equation 2. By equation 2, once again by equation 2, 2y square plus x square minus 3x times y plus x plus 3x square equal to 0. But in this case we have x equal to 0. That gives us 2y square equal to 0. So y equal to 0. But we don't get anything new. X comma y equal to 0. That's already taken care of. That's a trivial solution. We ignore it. Or that's already taken care of by previous solution. Case 2. So the case x equal to 0 turned out to be a trivial case. What about x equal to 8? So we get 2y square. 2y square. When I write x equal to 8, 8 square is 64. 64 minus 24 is 20. And then this one is 64 into 3. So in this case we get 2y square plus 20y plus 200 equal to 0. We can take 2 common to write y square plus 10y plus 100 equal to 0. Oh. So yeah, I made a mistake here. 8 square is 64 minus 24 is 40. And 40 by 2 is 20. So y square plus 20y plus 100 equal to 0. That gives us y plus 10 whole thing square equal to 0, or y equal to minus 10. So in this case we see that x comma y equal to 8 comma minus 10 is a solution. Let's look at case 3. Case 3, we take x equal to minus 1, so replace x by minus 1, so 2y square, minus 1 square, minus 3 into minus 1 into y, plus 3 into minus 1 square, minus 1, yeah. 2y square as it is, minus 1 square is 1, and minus 1 is plus, 3 plus 1 is 4y, this is 3, 3 minus 1 is 2, equal to 0. That gives us y square plus 2y plus 1 equal to 0. Again, this is of the type y plus 1 whole thing square equal to 0. So y equal to minus 1. Last case we take x equal to 9. Again by equation 2. 2y square as it is. 9 square is 81. 3 into 9 is 27. And then 9 as it is. And 3 into 9 square, 3 into 9 square. That gives us 2y square, 81 minus 27. That gives us 2y square plus 54y plus 252 equal to 0. We can take 2 common, so y square plus 27y plus 126 equal to 0. Okay, now this is a quadratic equation. Maybe we can factorize it. 126 can be written as 2 into 63. That's equal to 2 into 7 into 3 into 3. We want 27, so 6 into 21. Okay. So y square, 27, we will apply splitting by middle term method. 27 can be written as 6 plus 21. And 126 can be written as 6 into 21 equal to 0 as it is. That gives us y square plus 6y plus 21y plus 6 into 21 equal to 0. We take y plus 6 common, and then y plus 21. You see that we are following splitting by middle term method. So y equal to minus 6 comma minus 21. Therefore, in this case, x comma y equal to 9 comma minus 6 and 9 comma minus 21. So now we conclude that we have final solution x comma 0, that's a trivial solution for any integer x. Case 1 we don't have to write because we got x comma y equal to 0 comma 0. Case 2, 8 comma minus 10, 8 comma minus 10. Case 3, minus 1 comma minus 1. Case 3, minus 1 comma minus 1. Case 4, 9 comma minus 6 and 9 comma minus 21. So these are the solution 1, 2, 3, 4. Of course, we have infinitely for any integer x. For any integer x. These are the solution.